Okay, everybody, to start off today's work on inclined planes, which is really just an AKA for ramps. That's what we're doing. So any calculation that involves ramps in physics is called an inclined plane, more of a fancy term for it. There's two things that I want you to write down before we even begin here, just to remember some key concepts about the theory behind this. First of all, normal force. The reason why normal force is called normal, if you think back to grade 11, is not because it's regular. Normal means 90 degrees to the surface. And that's very, very important for today's work, to realize that normal forces are always 90 degrees to the surface. And friction is the only force where you always know what direction it's going to be in no matter what, because it always opposes motion. Always opposes motion. Okay, so we're going to go through a little breakdown for how forces are going to work on a ramp. And I'd like to do it on a computer screen. I know there's better ways to do this instead of pointing the video camera at a computer screen, but the fastest, easiest way to do this right now is just to do this. And no, I'm not going to bother making a screen capture video. I'm just going to point the camera at the screen. And we're going to go through this so that hopefully you understand it. So I'm just going to draw forces on this diagram. Now I don't want you to copy this. I want you just to watch this and think about this. So let's label our forces. If you have a 20 kilogram object sitting on a ramp, here are the forces that you're going to have. I put an X and a Y axis on there, the same as we always have. And here are my forces. So first of all, you have to have a force of gravity directly down. You can't escape that. That's because of the Earth, and that's because of the dimensions of the Earth. So directly down. There has to be a normal force, and again, the definition of normal is it has to be 90 degrees to the surface. So because of the tilt of the ramp, that gives us a normal force that no longer points straight up in the air like it did in grade 11. It's pointing up in the air on an angle. And if this box, this 20 kilogram mass, was allowed to slide down the ramp, there would be friction in the direction opposing motion, which, because of the tilt of the ramp, also comes out on an angle. So here's the problem. If you follow what I was saying at the start of this course, that every time you start a question in grade 12 physics, the very first thing you do is break up any force that's on an angle. The problem is, on this diagram here, you have two forces that are on angles. We would have to break up the normal force into two components, a vertical and a horizontal component, and we'd also have to break up the force of friction into two components. That could be done. It's not like it's impossible work, but we'd have to do work for two different vectors before we even begin. Reconsider something. What if you tilted the X and the Y axis? What if you thought of the X and the Y axis like this instead? Which sort of makes more sense, because the surface of the ramp where things are going to move, let's say left and right, doesn't look like this. It actually looks like this. So if we tilt the X and the Y axis and imagine it like that, and think of this question again, let's go through these forces again. So there's gravity straight down. There's a normal force that is 90 degrees to the surface. And when the box begins to slide down the ramp, there would be friction opposing motion in the opposite direction. So just by tilting the ramp sort of mentally in our head, not tilting the ramp, sorry, tilting the axis temporarily in our head, we actually only have one force that ends up being on an angle. And it's strange because it's actually not on an angle, it's directly down. But in the context of the way this axis is tilted, gravity would be the only force on an angle. So we could break the force of gravity into two components. And whenever you have a ramp, whatever angle is given in the bottom corner of the ramp would be the exact same angle in here. I don't want to go through the geometry for it, the Z patterns and C patterns or whatever. But in very short order, if you try to prove this mathematically, the angle in the bottom corner of the ramp would also be the angle inside this triangle. So we can break the force of gravity up into two components using that 30 degrees or using whatever angle is in the bottom corner. these are the two things that we are going to use. We're going to break gravity up into a x component, which is horizontal to the x-axis, and a y component, which is along the y-axis. And that's what we're going to use for ramps. This component right here, the x component, remember, you can draw vectors anywhere on a diagram. That component of gravity is exactly what is responsible for the box sliding down the ramp. So I'm going to pick this up, and I'm going to move it up here just for the sake of it making more sense. Okay, so here's our forces on a ramp. We've got a component of gravity that slides the object down the ramp. There's friction, there's a normal force, and there's also this component of gravity that is pushing the object into the ramp, and that is what the normal force is going to be, but more on that after. This you should probably draw on the page. Let me see what else I have on here. This is what the diagram of all the forces on the ramp look like. You can actually ignore this force of gravity right there. So you've still got 4 forces. 2 components of gravity, friction and normal. The y component of gravity and the normal force are going to cancel each other out, the same as they do in grade 11. And really the only 2 forces then on a ramp that are going to become important are these 2. We're going to deal with not the force of gravity, but only the x component of gravity as it slides down the ramp, and friction is going to hold it back. And really, that's it. The questions are going to very closely resemble questions in grade 11 where objects were flat on the ground and they were moving back and forth, but the formulas are going to change slightly because of the ramp itself. And let me show you on the page what that means. Okay, so down to this word now. So we're going to do a little bit of memorizing here, which is a word that I absolutely hate, but I don't want to go through the entire derivation for these forces. Because of COVID and because of the shortness of this, I'll allow the derivation to happen at a different point. So let me just say this. Whenever you have a ramp, you definitely have a horizontal component of gravity down the ramp because of breaking gravitation up into 2 components. The horizontal component of gravity is always here. It's the force of gravity times the sine of theta. So it's mg sine theta. You can always label that. It's always there and it's always down. There's no way that that is ever going to be up the ramp. Gravity always pulls things down. So mg sine theta. The force of friction, I'm going to label that on there. Force of friction, remember, has a formula. No matter what, force of friction formula is coefficient times normal force. That hasn't changed. However, the normal force on a ramp is 90 degrees to the surface. So the normal force on a ramp points up like this, 90 degrees to the surface. It no longer opposes gravity directly. It opposes the component of gravity when you break gravity into two components. So it opposes mg cos theta. Now, same idea as in grade 11. This much force, mg cos theta, is trying to force the mass into the ramp, and that's what the normal force has to be. So normal force is also equal to mg cos theta, and they cancel each other out, and we never have to worry about them in questions. Just theoretically, the idea is they're there and they cancel each other out. But it's important to know that because the force of friction formula is coefficient times normal force, and the normal force on a ramp is not the same as it is in any other question. It's mg cos theta. So in short, the force of friction on a ramp is coefficient mg cos theta. Now, you can memorize this result for a ramp. You can memorize that there are 2 main forces that you're going to use whenever you have a ramp. There's always going to be gravity down, mg sine theta, and there's always going to be friction, coefficient mg cos theta. It doesn't necessarily point up though. It always opposes the direction of motion. Sometimes you get questions on ramps where the mass is going up the ramp. Maybe it's being pulled up a ramp. Maybe it was shot up the ramp and it's sliding to a rest. If an object is moving up the ramp, then force of friction will be opposing motion on the other side. And there's a question like that, so we'll get to something like that. If this sounds confusing, let me show you how easy it is. Let's do an example here at the bottom of the page. It says the coefficient of friction is 0.2 in the above situation. When the box is released, what will be the value of the acceleration? There's a typing error. That's not supposed to be there, but what will be the value of the acceleration be? So nothing has changed. Acceleration is what it has always been and always will be in any physics that you do. It's net force divided by mass. And that's it. However, no matter what question you're doing or what physics you're doing or what unit you're in, net force is always found differently. And it's the net force on a ramp that's going to be new. So on this question, again, these two forces cancel out and we don't need to worry about them. There's two forces that are going to comprise the net force. There's a force of gravity down the ramp, and we assume that's the positive direction in this question, because it's the 20 kilogram mass is definitely going to slide down. It's not magically going to slide up the ramp. We let it go, it's going to slide down. So we'll use this as the positive value, and friction is going to hold it back to some degree. So remember, there's no formula for net force, no guaranteed formula anyway. You build the formula yourself, looking at diagrams and seeing what happens. So in this case, our net force is going to be mg sine theta minus the force of friction, coefficient mg cos theta. And that's it. If you sub into those individual forces and subtract the numbers, you will get the net force in this question. However, we're dividing by mass in the end. And actually, there's an m in every term. So just coincidentally in this example, even though we know the mass is 20 kilograms, we don't even need to use the 20 in this example. Mass cancels out, and actually when mass cancels out, the whole fraction is gone as well. All we have are some things on the top. So let's sub in. G is still the regular value for G. It's never going to change. So 9.8 meters per second squared is still here. We're going to multiply it by the sine of the angle, and that's always the angle in the bottom corner of the ramp, so sine of 30 degrees minus, and maybe I'm going to use a set of square brackets here because I don't want to forget to multiply all this together before I subtract it. The coefficient of friction is given as 0.2. G shows up again. I suppose maybe I could have pulled it out as a common factor first and shortened this a little bit, but oh well, so what, too late now. 9.8 cos of 30 degrees. Again, I want to make sure I do all this first. Make sure your calculator is in rad mode. Yeah, no, make sure your calculator is not in rad mode. Make sure your calculator is in degree mode. And you should follow through with this calculation. Don't just write down the answer and move on. You should grab a calculator and make sure that you are going to get the correct answer. I'm just doing it here off screen, and that gives you a chance to do it too. And I didn't get the right answer, so let me do this a little bit slower. This happens all the time. I'm going to start with the second term. So I'm going to do the cos of 30 first. I'm going to multiply it by 9.8 and multiply it by 0.2. So there's my first term. I'm going to have another line of work here. What the heck? Minus 1.6974. And the first part, 9.8 multiplied by 30 sine, 4.9. Okay, so the final answer in this question is 4.9 minus 1.6974. We get a final answer of 3.2 meters per second squared. So not only is this the answer, but just like in grade 11, I can think about this a little bit and make sure the answer is correct. See, there's a few things about this that make it correct even without checking the math. Number one, this is an object on a ramp. If it was a free-falling object, if you just took a 20-kilogram mass and dropped it, the maximum acceleration that it could have is 9.8. You can't exceed free fall acceleration when something is moving downwards. But there's a ramp in the way. There's definitely friction. So number one, this answer is correct because it's less than 9.8. So it's accelerating less than if it was just free fall. And I guess number two, I'm a little bit more advanced on this than you are just starting off. I'm looking at that 30-degree angle and the amount of friction, and I can kind of surmise a few things from that. It's a 30-degree angle is not very steep. So to me, this 3.2 meters per second squared is at the lower end of what acceleration could be. It has to be between 0 and 9.8 for a question like this, and that sounds right for a couple of reasons. More on that as you get more advanced in these questions. Let me flip the page to the back. Sorry, a little bit is gonna bleed through here. We're gonna do two more examples. And yeah, the video is gonna be a little bit long, but I'm trying to take this slow so that you at home have an easier time with this. So let's see what happens if there isn't a diagram. And that shouldn't confuse you. There was a video to go with this, but you don't need to watch the video. It says it was a person sliding down the banister of an escalator, if you can picture that. Maybe I'll put the link under this video. But yeah, it was somebody climbing up onto the handrail of an escalator and sliding all the way down and falling off the bottom. So here it says the banister on an escalator is 15 meters long. Let me just draw that and label it as 15 meters. So that distance is 15 meters long, and it's elevated at a 50-degree angle. So here's our ramp. 15 meters long, 50-degree angle. Jerome sits on the top and slides to the bottom, taking exactly 2.5 seconds to do this distance. So consider a mass, it's a person. I knew his name was Jerome because he actually posted the video himself. A person sits here, this is our mass, slides all the way to the bottom, takes 2.5 seconds to get to the bottom, and the question here is solve for the coefficient of friction. So you want this, as he's sliding down the ramp, you want to know what's the coefficient of friction between his body and the ramp if it's going to take a time of 2.5 seconds to get all the way to the bottom. Well, that's a mouthful, and as usual, you're not going to know where to start that question when you first read it. So let me pick through a few things here. The very first thing you do when you're looking at a ramp question is you want to label forces on the mass, and it's on a ramp, so you can definitely label two forces, right? Same as the last question. Let's label our forces right away. You can definitely say that in the direction down the ramp there's going to be a force of gravity, mg sine theta. So again, that's a memorizable result for high school anyway. And as he slides down the ramp, there's going to be a little bit of friction between his pants or his body and the hand railing, and that friction is going to oppose motion and have a formula of coefficient mg cos theta. Again, something you can memorize. This mg is the force of gravity. The sine and the cos is from breaking the force of gravity into components in the previous diagram at the start of all this. But you don't have to go back to that. You can jump right to these two results when you're dealing with ramps. Okay? So you can calculate his acceleration. See, we almost have enough givens here. If you actually try and make just a regular grade 11 givens list and forget about the fact that there's a ramp here, because it's still a distance. It's just tilted up on an angle, and that angle is going to be dealt with these sines and coses. So think of it as just a sidewalk, even though it's tipped up on an angle. V1 is 0 meters per second. The time to go the full distance is 2.5 seconds, and the distance is 15 meters. Actually, we already have 3 givens. I was going to say, we'll work out the acceleration and we'll use that acceleration to find something, but now that I'm kind of talking my way through it, I realize we won't be able to work out the acceleration with these forces because we don't know this coefficient. So this question we're going to do backwards. We're going to start here. Start with the grade 11 stuff, and let's solve for acceleration instead. And then we're going to use that acceleration in our force formula, our net force formula, and the only unknown will be that coefficient of friction. So I can see how this is going to go now. Look at these variables and pick your grade 11 formula that doesn't have any V2 in it. It's going to be this one, D equals V1t plus 1/2 AT squared. We're going to solve for acceleration. That's not the easiest of rearrangements, but if you're interested in practicing as many rearrangements as you can, there's the rearranged formula, or at least my version of how I'd like to rearrange it. I'm going to sub in my variables as soon as I turn the lights back on. Sorry guys, that's going to be a reality in every single one of these videos. I have to sit at the desk to do this, and I'm by myself, and the lights will time out every single time. Distance is 15 meters. Subtract V1t, but V1 is 0, so actually that's just a subtraction of 0. Divide by 1/2 t squared. He slides down the ramp, it takes him 2.5 seconds. Alright, so quickly on a calculator. That's 15 divided by 3.125. Okay, so it's 4.8 meters per second squared. And again, that value makes sense because it can't be 9.8. 9.8 would be if he just dropped straight down. So he's on a ramp, fine. It's a value between 0 and 9.8. That sounds good. Okay, so now let's look at this. Those are the forces on the ramp, and that's how you would get your acceleration. Normally, you would say acceleration equals net force divided by mass. And you would look there and say, well, there's only two forces because the forces in the vertical direction cancel each other out. So acceleration would be mg sine theta minus coefficient mg cos theta. And we're not given Jerome's mass, but that's not going to be a problem in this question because you divide the whole net force by mass. And so mass cancels out. It's in each term. So acceleration will be g sine theta minus coefficient g cos theta. I don't want you to write that down as any kind of memorizable formula because it's really just for this question. Every question can end up having a slightly different formula, as you'll see in example 3. Okay, so let's sub into this. Actually, I'll do what I didn't do in the last question. G is a common factor, so I'm actually going to take that out just so I don't have to write it twice. Actually, you know what? My apology. That's not a good idea. Normally it would. It's a common factor. You can take it out. But we have to isolate. I forgot. We have to isolate for coefficient of friction. So ignore this. It's a little bit easier to flip that formula around instead of having coefficient of friction buried in a set of brackets. So, and I want to do this slow because I don't want to get it wrong. I'm going to bring over the g sine theta, make it negative. And that'll still leave the right hand side of this formula as negative. So I'm carefully watching that negative sign. I'm going to keep going. Actually, you know what? I'm running out of space here. But I'm going to bring over the negative g cos theta, and that would all go on the bottom. Negative g cos theta, leaving just coefficient of friction by itself. Be very careful, you can't cancel those g's. There are two terms on top, one term on the bottom. There'd have to be a g in every term in order to cancel it out. So you can't cancel it. I'm just going to sub in now. And for the sake of this video, I'm going to skip units because I'm running out of space here and I just want it to look a little bit cleaner. So acceleration, we figured it out as 4.8 minus, I'm going to put this in brackets because I want to make sure to multiply things together, 9.8 multiplied by the sine of 50 degrees was the angle in this question, divided by a negative sine, 9.8 cos 50 degrees. Okay, so be careful. The top is actually going to be negative when you work it out, and it'll cancel with the negative on the bottom. Now I'm going to do this carefully in the background. I want to make sure not to mess this up. So again, you should follow through on your own calculator though, because I want you to make sure that you can get this answer. And I already messed it up. I have to start it again. My apology. I hate when this happens on a video. I would rather have these answers worked out off to the side, but I don't want to do that because I'm hoping that you'll be working out the answers at the same time as me. Divide by 9.8, divide by cos 50 degrees. Okay, so the final answer in this question comes out to 0.43. And had I put units throughout the formula, everything would have canceled out and you get a unitless value, which makes sense because it's a coefficient of friction. So not only does this make sense because it's a unitless value in the end, but it's also like the numerical value there is a proper numerical value for a coefficient of friction. It sounds good. It's between 0 and 1. So I'm actually not even going to check this question. The acceleration answer made sense, and the coefficient of friction answer makes sense too, to me. So we have one more example to go through, example 3, but regular class is going to start in a minute. In fact, the first person just walked up to the door. So I'm going to stop this video and I'm going to start a second video just for example 3, and we'll continue.